Okay, let's have a look here at this question. There we go. Right, okay, let's see. Write down two linear factors of x squared plus y squared, and hence or otherwise find the two factors of 5 whose sum is 2. Factorize that and verify. Yeah, okay, that's interesting. So x squared plus y squared equals, let me write that a bit neater. X squared plus y squared equals x minus iy times x plus iy. Find two factors of 5 whose sum is 2. Okay, so I'm guessing we can say 5 equals 2 squared plus 1 squared. So that would be 2 minus I and 2 plus I. Okay, and hence factorize this. Okay, so I see what they're up to. They want us to factorize this, so we need. Okay, that's funny. I've not seen a question like this before, but I like it. So we need a product that adds the two numbers that multiply to make 5. Well, we know these two numbers multiply to make 5. And add to make minus 2. That's sad. They add to make 4. Oh, yeah, of course. Sorry, the sum is 2. So I've actually not successfully completed the last part. Alright, so it's not 2 squared plus 1 squared then. Okay. Two factors of 5 whose sum is 2. So could it be something like a 3 and a 1? Yeah, maybe it's 3 and 1. Or not 3 and a 1. 3 and a 2. 3 squared minus 2 squared. No, they don't add up to 2. Ooh, okay, this question's harder than I thought. How are they wanting us to do this? Write down two linear factors of x squared plus y squared. Okay, I've done that. And hence or otherwise find two factors of 5 whose sum is 2. Okay, well let's just do it the algebra way then. So you have alpha times beta equals 5 and alpha plus beta equals 2. So you have alpha equals 5 over beta, and if you put that in here, you get alpha. I'm replacing alpha, so that means you get 5 over beta plus beta equals 2. Oh, this is looking familiar. So that means if you multiply by beta, you get 5 plus beta squared equal to 2 beta. So that means you get beta squared minus 2 beta plus 5 equals 0. I see. So that's why it says hence or otherwise find the two factors whose sum is 2 and then factorize that. So by solving here for beta, and then we get the alpha. Okay, yeah, all right. Yeah. Beta is minus b plus or minus the square root of b squared, which is 4 minus 20. So that's minus 16 all over 2a. So that's 2 plus or minus 4i over 2. So that's 1 plus or minus 2i. So not, okay. Okay, I didn't even think about swapping them. Yeah, so I said 4 squared plus 1 squared. Actually, 1 squared plus 4 squared would have worked. So let me just clear that off and make that quite clear again. X squared plus y squared, that's equal to x plus iy times x minus iy. 5 equals 1 squared plus 2 squared, which will equal 1 plus 2i and 1 minus 2i. And if you add them together, 1 plus 1 is 2. And the I parts cancel. So that successfully completes the first part. And then to factorize this, x squared minus 2x plus 5, that's equal to 2 factors here. X minus and x minus. And we need two numbers that multiply to make 5 and add to make 2. So that's 1 plus 2i and then 1 minus 2i. Okay. And to verify your answer, I guess you could just multiply it out. I'm surprised that we have to do that, but okay, let's verify it now. So if we multiply this out, you get x squared. X by x is x squared. And then that's minus x plus 2ix. And then you multiply by minus 1. So that's minus x plus 1 minus 2i. And then you multiply by minus 2i. Minus 2ix plus 2i. And then minus 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 is minus. But then I squared is minus. So that's plus 4. So that cancels with that. That cancels with that. So you're left with x squared minus 2x plus 5. Good. That answers the first part. Yeah, actually, I haven't seen that one now. I'm going in reverse, going backwards in time. So that's the first time I've seen that question. I like it, actually. Let's have a look at the B part. Prove. Okay, so modulus of z is equal to x plus iy times x plus iy. Oh, sorry, no, modulus of z. Sorry. I'm looking at this right-hand side. So the modulus of z is the square root squared of x squared plus y squared. So the modulus squared is just x squared plus y squared. And then we calculate z by its conjugate. That's x plus iy times x minus iy. That will be x squared, and then the middle pieces cancel, plus y squared. So yeah, it's true. The same. Okay, and then we can do something similar for the next part. So z1, z2 conjugate is x1 plus y1i times x2 plus y2i conjugate. That's going to be x1, x2 plus x1, y2i plus y1, x2i plus y1, y2i squared conjugate. So that's going to be x1, x2 minus y1, y2 minus x1, y2i minus x2, y1i. And let's check what z1 conjugate times z2 conjugate is. That's x1 minus iy1, x2 minus iy2. That would be x1, x2 minus x1, y2i minus x2, y1i minus minus minus, so minus y1, y2, minus y1, y2, yeah, x1, x2, yeah, minus x1, y2i minus x2, y1i. Yep, it's the same. Okay. Deduce. Right. So z1, z2, z3 conjugate. That's equal to z1, z2 as a term times z3 conjugate. And then you can use your result in 2 to say that will be z1, z2 conjugate times z3 conjugate. And then you can use your result in 2 again to split the first one. z1 conjugate, z2 conjugate, z3 conjugate. So that's equal to z1 conjugate, z2 conjugate, and z3 conjugate. Okay. Fz is a cubic and z1 is a root. Prove that z1 conjugate is also a root. So you know that a0 z1 cubed plus a1 z1 squared plus a2 z1 plus a3 equals 0 since it's a root. So that is a0 z1 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 plus a1 z1 z1 plus a2 z1 plus a3 equals 0. So you can say the conjugate of this is equal to the conjugate of that. And you can split the conjugate up. So it's conjugate of a0, conjugate of z1, conjugate of z1, conjugate of z1, conjugate of a1, z1, z1, a2, z1, a3 is equal to 0. But because a is real, its conjugating it doesn't affect it. So that's a0 z1 conjugate cubed plus a1 z1 conjugate squared plus a2 z1 conjugate plus a3 equals 0. So therefore z1 conjugate is a root. Okay. Right. And then lastly, you're given one root and you want the other two roots. So you know that the roots occur in conjugate pairs. So that means 2 minus 3i is a root. And note that 2 plus 3i times 2 minus 3i is equal to 4 plus 9, which is 13. And 2 plus 3i plus 2 minus 3i is equal to 4. So the cubic 3z cubed minus 13z squared plus 43z minus 13. It definitely can factorize to a quadratic. And the quadratic has two roots. And the two roots must be 2 plus 3i and 2 minus 3i. And to form a quadratic with those two roots, the quickest way to do it is to say that it's the quadratic z squared minus the sum of the roots plus the product of the roots. And you can see what the last bracket here must be, because when you multiply these out, you should get minus 13 at the back. So that has to be minus 1. And when you multiply the first by the first, you're supposed to get 3. So you have here 3z minus 1. So therefore, the other roots are the conjugate, 2 minus 3i, and 1 over 3. That looks like what the other roots are. You could test it out if you want. You could put in 1 over 3 here and make sure you get 0. Let's see, 1 over 3 cubed is 1 over 27, so that's 1 over 9. So I wonder if I got a crude calculator here. 1 over 9, okay, minus 13 over 9. Oh, this calculator's not working properly. Minus 13 over 9 plus 1 over 9, and then minus 13, and then plus 43 over 3. So does 43 over 3 look like that number? Yeah, it is. Yeah, good. Yep. So it works. It works. Okay, kind of a long question. Very proofy question. Lots to prove in it. A was a bit tricky. Yeah, and actually I took a shortcut in finishing the last part here. Some students might want to do a long division even. So yeah, it's kind of a long question actually. I had to use some shortcuts to shrink it down a bit, and I had to think about A for a little bit. So good tough question. All right, we'll wrap that one up there.